Hi everyone, so welcome to this video. So in this video we will try to understand the physics behind the movement of a car or any vehicle on the road. Well, most of us most of you who would know how to drive a vehicle, or most of us in general would know that a car has an engine. Now that engine produces power, which in turn produces torque on the wheels of the vehicle, and that torque makes the wheels of the vehicle rotate. Now as the wheels of the vehicle rotate, the car moves, right? The car moves linearly. Now how does this torque, which leads to a rotational motion, which in a way makes the wheels rotate, how does that torque makes the vehicle move linearly, right? Because the torque leads make the wheels rotate, right? But our car moves linearly. So how does that happen? So that is what we will try to understand. And second thing is, again, what happens when you increase torque? Well, again, common wisdom says that as you increase torque, the speed of the vehicle increases, right? So let's say you keep on increasing torque, the speed of the vehicle will increase at the same rate, right? Now, and again, practically most vehicles have an upper limit to the amount of torque which the engine of the vehicle can produce. Right? But let's say theoretically you have a vehicle which could produce a very large amount of torque. Let's say, for argument purpose, let's say the vehicle could produce an infinite amount of torque. Now let's say gradually you start from zero torque, and then let's say you increase the torque gradually, and then you keep on increasing it. So of course the speed will increase. But let's say you continue increasing the torque to infinity, right, or to a very large value. What will happen? Will the speed of the vehicle also continue to increase at the same rate, or will the speed of the vehicle be different? So common wisdom will say that as long as the torque is high, the vehicle will continue to move at the same rate at which the torque will increase. But let's see whether that is true. So these are some of the sort of questions we will try to answer in this video. And in a way, in this video we will cover all aspects of mechanics. So this is kind of a crash course of mechanics. Here we will cover the linear motion, all the aspects of rotational motion, friction, torque, which we have been discussing, angular acceleration, linear acceleration. So all the concepts of mechanics, more or less, we will discuss. So to start the analysis, so let's kind of draw the free body diagram of the wheel, like of this wheel of the vehicle, because ultimately the whole pressure, the whole load kind of occurs or acts on the wheels of the vehicle, because the car is in contact with the ground through its wheels, right? So let's for our analysis we will have to consider the wheels. Now there are 4 wheels. So let's say we could do this analysis on each of the wheels, and we could analyze this car in that way. Maybe for simplicity, we will assume we will consider one wheel, and we will assume that this wheel is representing the entire car. This wheel is kind of having the weight of the entire car. So we will analyze this wheel, but it will be in a way the analysis of all the 4 wheels together. So if we draw the free body diagram of this wheel, so what are the forces which will act on the wheel? So of course, first will be the weight of the car, right? Then the normal reaction from the ground, which will be in opposite direction, which will balance the weight. Then there will be a torque due to the engine, right? The engine will apply some torque. Now because the engine will apply some torque, and for the time being, let's assume there is no friction, then what will happen? The engine will apply some torque. Now because of the torque, this vehicle will tend to rotate. So let's say this vehicle is in contact with the ground at this point P, right? And for the time being, let's assume that this tire is solid. When I say solid, what I mean is that this tire is non-compressible. So this tire is touches the ground at one point P. Well, practically, that's not the case, because practically the tires are slightly compressible. So at the point of contact is not just a point, but the tire slightly flattens, right? But for the time being, let's assume that this is a solid tire, and it's non-compressible, so it touches the ground at one point P, right? So because of the torque of the engine, this and let's say friction is not there for the time being, this tire will tend to rotate. Now as this tire will tend to rotate, so this point P at which it touches the ground, this point P will also rotate. But so in a way, this point P will tend to move in this direction, right? This point P will tend to move in the negative direction. Now because this point P will tend to move in negative direction or move in this direction, so this point P will try to slide. The point of contact will try to slide in the backward direction, and because this point will slide, so friction will come into play. So friction will try to oppose that motion. So force of friction will act in the opposite direction because it will oppose that sliding motion, right? So the force of friction on this tire will act in the opposite direction, right? So this is the free body diagram of the tire. Now as we can see here, this force of friction, right? This is the force of friction which kind of makes the vehicle move in this direction, in the linear direction. Because you see, in this free body diagram, there is no force which acts, in the linear direction. So weight and normal reaction acts in vertical direction, and they cancel each other. The torque which acts on the vehicle makes it rotate, but because of which force of friction comes into play, which acts in the opposite direction, and it makes the vehicle move in this direction. Right, so we have answered our first question. So that how the vehicle moves in a linear direction when it comes, and when the engine applies torque, because friction comes into play, and it's the friction which actually moves the vehicle in the linear direction. That's number one. Number two, let's consider this point P in more detail. Now we can see that there are two motions now in the vehicle. One is the rotational motion, which is caused by the torque of the engine, right, which causes the wheels to rotate. And then there is a linear motion, which is because of the friction, which causes the vehicle to move in the linear direction. So there are two motions at play, rotational motion and linear motion, right? Now let's consider this point P. So this point P has two motions, and not only this point P, each point on this tire has two motions. So the net motion of each point of the tire is the superimposition of the linear motion and rotational motion. But let's focus on point P for the time being, because that is where the rubber meets the road. So because of the rotational motion, this point P has a tendency of moving in the backward direction, and because of the linear motion, this point P has a tendency of moving in the opposite direction, right? So the net motion of this point P is the superimposition of the rotational motion and the linear motion. So this is very important, and on this point we will come back in a bit. Now, as we discussed, so the two motions are happening, rotational and linear motion. So let's analyze the rotational motion first. So in rotational mechanics, what is the equivalent of Newton's second law? So in linear motion, we know Newton's second law says that force is equal to mass into acceleration. So in rotational mechanics, we know the equivalent equation is torque is equal to moment of inertia times angular acceleration. So torque is the equivalent of force, moment of inertia is the equivalent of mass, and angular acceleration is the equivalent of linear acceleration. So torque is equal to I alpha is analogous to force is equal to mass into acceleration. So what is the net torque which is acting on the wheel? So the net torque is the torque which is due to the engine, which is tau, and this force of friction also acts. Force of friction also produces a torque. So let's say we are analyzing this rotational motion from the center of the wheel. So if our axis of rotation is the center of the wheel, then about the center of the wheel there is a torque due to the engine which acts in clockwise direction, and then there is a torque due to the friction which acts in the counterclockwise direction. So what is the torque due to friction? That is equal to force times the radius of the wheel. So the net torque on the wheel will be tau minus Fr. That is the net torque is equal to moment of inertia of the wheel I into alpha. And here again, to repeat, we are considering all the four wheels together, right? The same analysis could be done on each of the wheels, but we are assuming that this analysis we are doing on one wheel takes into account all the four wheels together. Then what is the angular acceleration? So that will be tau minus Fr by I. Now, so this tire has an angular acceleration. Now, once the tire has an angular acceleration, so its angular velocity will increase. We know that angular velocity is equal to omega is equal to omega naught plus alpha t. Here we are assuming that the vehicle was initially at rest, so the initial angular velocity was 0. So at any time t, the angular velocity of the tire will be equal to alpha times t. Right? Now, so this wheel will have an angular velocity. Now because of the angular velocity, as we discussed, this point P will also, and each point will also have a linear velocity also, right? Because that we have seen in circular motion. When an object moves in a circular path, it has angular velocity, but each point also has a linear velocity, right? So this point P also has a linear velocity, and the linear velocity at this point P will be tangential to this point P, and it will be act in this direction, right? So what is the linear velocity at point P? So that V will be equal to R omega. r times angular velocity, right? And omega is equal to alpha t. So if we put all this equation here, we get the linear velocity at this point P because of the rotational motion of the wheel in the negative direction or in the backward direction is r torque minus Fr divided by I into T, right? Now, as we discussed, this point P will also have a motion in the linear direction in the forward direction, right? And the net motion of this point P will be the superimposition of both the motions. So, right, so now having considered the rotational motion, let's consider the linear motion. Now, in the linear motion, which is let's say in the forward direction, there is only one force, which is the force of friction. So, force of friction, force is equal to mass times acceleration. So, m is the mass of the car and a is the linear acceleration of the car. So, what is a? A is equal to force F by m. And what is the linear velocity of the car? That is equal to v is equal to at, and that becomes F by mt, right? And we know that force of friction is less than equal to mu n, right? So mu n is the maximum force of friction, but force of friction, is not always equal to mu n, right? I mean, that's the maximum. Mu n is the maximum value, and that force of friction attains when the need comes. But when the need is not there, the force of friction will be less than equal to mu n. So the maximum linear velocity of this of the car will be at any time t will be mu n t by m, right? So this will be the kind of the maximum linear velocity. But in force of friction term, the linear velocity of this point P will be F by m into t, right? Now, so now again to repeat the point, because of the rotational motion, this point P has a tendency to move in backward direction, and because of the linear motion due to friction, this point P has a tendency to move in the forward direction. Now, when we drive the car on the road, we don't see the tires of the car skid on the road. And what do we mean by skidding? So to visualize skidding, let's say you are driving or you are driving in a muddy road, or you are driving in a muddy area. Then most often you would see that the tire skid, because what happens, your tire will start to move in a very at a very high angular velocity, but the vehicle doesn't move, right? So the tire starts to skid. But in general, when we drive on the road, we don't see the tire skid, right? We see a very smooth motion. There is no skidding at all. So what does that mean? So that means that this point P actually, when we say this point P does not skid, it means that this point P, like the relative velocity of this point P with respect to the ground is zero, right? Because if the point P would have skidded, then either it would have skid in the negative direction or it would have skid in the positive direction, right? But because it does not skid, it means that this point P with respect to the ground does not slide, right? This point P with respect to the ground remains at rest. And try to visualize this. When the car moves, it moves slowly, right? We don't see the tires skidding, right? That's very important. And mathematically, what it means that the point P does not slide, and the point P, the velocity of the point P with respect to the ground is equal to zero. Now, why will the velocity of the point P with respect to the ground will become zero? Because we have seen that this point P has two opposing motions. One motion which makes it move in the backward direction because of torque, and one motion which makes it move in the forward direction because of friction. So, for the point P not to skid, both the motions should cancel each other. And that state, when the point P does not skid, is called pure rolling, right? It's called pure rolling. So for pure rolling at point P, the velocity in the backward direction because of torque, which we have seen is r times tau minus Fr by I into t, should be equal to the velocity due to the force of friction, which is F by mt. And then from this we find that the force of friction is equal to mr tau divided by I plus mr square. and then we know that the force of friction is less than equal to mu mg. So this gives the value of torque, the maximum, the value of torque tau should be less than equal to mu g. This term, if you solve this, if you force of friction should be less than equal to this, so this whole term should be less than equal to this. And if you know what is our goal? Our goal is to find the maximum value of torque which can be applied on this vehicle such that the vehicle does not skid, right? So for that, if you kind of do the cross multiplication, so tau will become should be less than equal to mu g I plus mr square divided by r, right? And let's assume that this wheel is a disc, solid disc. So I is equal to, for a solid disc, the moment of inertia is mr square by 2. So if you put that as the value of I, so your torque should be less than equal to 3 by 2 mu g mr. So what does it mean? So it means that for your vehicle to not skid, the torque should be less than equal to 3 by 2 mu g mr, right? So let's say initially you start your vehicle, and so when you start the vehicle, the torque will be 0, but immediately when you start, you will apply some torque. So the torque will increase. So as your torque will increase, so that torque will lead this point P to move in back direction. But then as the torque increases, the force of friction also gradually increases, and the force of friction compensates the effect of the torque by making sure that this point P becomes 0. So as the torque increases, the force of friction also increases. And mind you, the force of friction at that instant is not equal to mu n. Force of friction is less than equal to mu n. So force of friction has some value, but it is less than equal to mu n. So the torque increases, force of friction also increases, and force of friction counterbalances the effect of torque such that this point P remains at rest, and this point P does not slide. And this can happen till the torque is less than equal to 3 by 2 mu mgr. Till that instant, the force of friction will be able to counterbalance the effect of the torque. If the torque increases beyond this value, then what will happen? The rotational motion will overpower the effect of rotational motion at this point P will overpower the effect of translational motion because of the friction. So then skidding will start. Then what will happen? The negative velocity, the velocity in the backward direction will start to become larger than the velocity in the forward direction. And then the tire will start to skid, right? And that's what happens in the example we took, where let's say a car moves in a muddy road or in a muddy area. You apply a lot of power, the vehicle skids, right? So why that happens? That happens because you are applying a very high torque, and the torque value possibly becomes more than this 3 by 2 mu mgr, and because of that, the vehicle starts to skid, right? Another thing to note there is that mu, so this maximum torque depends on, of course, mass of the vehicle, radius g, but also mu, friction, right? So if the friction between the road and the tire would be high, the torque, you could apply higher torque, you would be able to apply a higher torque such that the vehicle does not skid. But in the muddy area, the friction is very low, right? Because friction is low, the maximum value of the torque is less, and so the threshold is less. So easily your maximum torque you will apply becomes more than the threshold, and your vehicle starts to skid. Let's visualize this with the help of a graph so that we understand this point better. So we know that torque should be less than equal to 1.5 or 3 by 2 mu g mr. So let's apply some real values. So in general, the value of friction on the road when a car moves is somewhere around 0.7. G is around 10 meter per second square, or actually 9.8 or 10 meter per second square. M is the mass of the car. So on an average, a decent sized car will have a mass of 110,000 kg, and the radius of the wheel would be on an average somewhere around 230 centimeter, 0.23 meters. If you apply all this value, then on a normal road for an average car, the maximum torque the maximum torque you can apply on the car should be less than equal to 22,300 Newton meter, such that the car will not skid. Now let's look at the specification sheet of our average cars we use in our home. Most often the maximum torque limit is what? It could be around 80 Newton meter, 100 to 120 Newton meter. For sports car, it would be around 600, 800 Newton meter, for the Ferraris and all of the world. So that is much lower than the maximum permissible limit of the torque. So that's why on a Ferrari also, if you keep on increasing torque, your velocity will keep on increasing, right? Because the upper limit is very high. So let's visualize this in a better way with the help of a graph. So let's say this yellow line on this graph is the velocity of this point P in the backward direction because of the rotational motion, and this blue red line is the velocity of this point P because of the force of friction in the linear motion. And we know that both these velocities are opposite to each other. So till the point of no pure rolling, both these velocities cancel each other, so that this point P remains at rest. So let's say when you switch on the vehicle at t is equal to 0, the torque will be some value, much less than this value, of course. So the torque will, you will apply some torque, so the backward velocity will increase like this, and so the force of friction will also increase to compensate the torque. Again, remember, force of friction should be less than or equal to mu n. So force of friction will increase to compensate for the torque, and this will go on till the point this torque becomes equal to 1.5 mu gr, and at that instant force of friction will also be maximum, which will be equal to mu n. Now after that, if you increase the torque further, you see the backward velocity because of torque will increase more than the linear velocity because of the force of friction. And so since the backward velocity increases, the vehicle will start to skid, right? And your linear velocity, so it's not that the linear velocity will not increase, linear velocity will also increase because force of friction will still act, right? But your linear acceleration will now become constant. What will be your linear acceleration? And beyond this point, the force of friction will be equal to mu n. Force of friction will be equal to mu n, and what is n? N we know is mu mg. So what will be the linear acceleration? That will be equal to force of friction by mass. So which will become equal to mu g, right? So beyond this point, when the torque increases more than this point, you see the linear acceleration becomes constant. So the vehicle speed will linearly increase, but the acceleration becomes constant. It becomes independent of mass. So what does it mean? So let's say initially you were driving the vehicle and let's say you had 5 people in the vehicle. Beyond this point, since your linear acceleration becomes constant and it becomes independent of mass, so let's say of those 5 people, you drop 3 people, and let's say you just have 2 people in the vehicle, still your velocity will not change. Your velocity will remain unchanged, right? So your velocity becomes independent of the mass. It's counterintuitive, right? Like in general, in a vehicle, if you put more people, if you put more load, then of course the velocity will decrease, right? Because the load increases. So for the same power, the vehicle needs to do much more work, right? But now beyond this point, the speed of the vehicle becomes independent of mass, right? So whether you have 1 person or whatever, or you have 5% or 10%, the vehicle speed will not change. It will increase, but the speed will become independent of mass. So this is kind of slightly counterintuitive, but this is one observation which will come into play when your torque becomes more than the threshold upper limit, right? But for all practical purposes, the cars which we have, even the most advanced sports car and all, the maximum torque is less than the maximum this value 1.5 mg/mr. But again, if you have a very less friction on the road, then this maximum value will be lesser. That's why the roads are made rough. Even if you have those concrete roads and all, there you will see artificially the roads will be made slightly. There will be some sort of scratches and all will be given on the road such that the friction remains high. So yeah, that's all in this video. So hope the mechanics of the motion of a car on the road would have been clear. And in this video, mostly we have covered all the aspects of mechanics. So yeah, thank you. Thanks for watching.